M1 Statics example 7. In this scenario, we've got a particle lying on an inclined plane. It's a smooth plane, so we don't need to worry about friction. And it's inclined at 45 degrees to the horizontal. As soon as I see the angle here, I'm also starting to think about what other angles will be 45 degrees. And you may remember from previous examples that if this is 45 here at the bottom, then this one here, which is between the vertical and the perpendicular to the plane, that one will also be 45 degrees. Now in this case, we've also got an additional force, P, which is being applied to the particle horizontally. And you may remember from your maths at school, angle properties, you might call them Z angles here. They're actually called alternate angles. And so this angle here will also be 45 degrees. So it's worth thinking about that when you read the question. We've got a cable going over a smooth pulley, and then we've got a 1 kilogram mass which is freely suspended at the other end. So I've drawn all the forces on. There's a tension which will be the same throughout the string, a normal reaction which will be at 90 degrees to the surface, and the weight acts vertically downwards. Now the system's being held in equilibrium, which means that it's being held stationary in this case. So when we're trying to work out the magnitude of P, we need to be starting to think about all the forces that are acting on this particle. So we've got T, we've got R, we've got the weight, and then we've got this force P. Now if you think about acting along the plane, along the inclined plane, we've got tension, we'd have a component of the weight, and we'd also have a component of this force P. So if we were to do F equals ma up the plane, then we'd have T that acts up, and then down the plane we'd have 3g sine 45, because you're turning away from the 45-degree angle, and then you've got P cos 45. And those forces must balance because this object is in equilibrium. So any forces up the plane would be equal to any forces acting down the plane. Now in this, we've still got another unknown. We don't know what T is. We're trying to calculate what P is. But if you look at the particle here that's hanging freely, if we were to do F equals ma vertically for this 1 kilogram particle, we've got tension upwards, and we've got the weight, which in this case is just 1g, acting downwards. So we can actually calculate the value of g. So if we put that in there, g equals 3g sine 45 plus p cos 45. So if we rearrange that to make p the subject, it'll be g minus 3g sine 45, and then if we divide that through by cos 45, that'll leave us with p on the right hand side. So I've done 2 steps in one there, so just check that you follow that particular step, and when you type that into your calculator, p works out to be 16 newtons to 2 significant figures, but keep the full value in your calculator just in case we need it in the second part of the question. So that's part A. We've worked out the magnitude of P, which is basically just the size of P. We now need to find the normal reaction between the mass and the plane. So in other words, we need to find this force R. So we're going to be doing F equals ma perpendicular to the plane. Because there isn't any acceleration, that means that forces upwards and forces downwards will balance. Now we've got to be really careful because there are actually 3 forces acting perpendicular to the plane. Upwards, we've got R, and then downwards we'll have 3g cos 45, that's a component of the weight, but we'll also have a component of this force P, and that will also act downwards because if you resolve to the perpendicular, the arrow will be pointing downwards, so it's acting in the same direction as the weight. Now we know the value of P, hopefully you've saved the full value in your calculator from earlier, so if you substitute that in and work it out in full, it should work out, I think, to be 32 newtons to 2 significant figures.